In this video, I will explain 4 of MATLAB's more esoteric commands. Commands which might not occupy a place in your repertoire like those more commonly used by ODE students. For example, dsolve, EasyPlot, or ODE45. But these commands, these 4, which nevertheless can prove useful in solving some of the problems from the differential equations with MATLAB book, aka DOOM. The 4 commands are eval, deval, BVP4C, and deal. In each case, I'll describe the command, more or less how you would encounter it in the help files, and then I'll discuss its syntax, and finally I'll present an instance in which it may be used, the command may be used to solve a problem from one of the problem sets in DOOM. We'll discuss the second, that is deval, and the third, BVP4C, together, since I'll present a joint application, and I'll discuss the last, that is deal, in the context of event detection, which is a very useful feature of MATLAB that I examined in a prior video. So, as usual, we clear everything before we start, and let's consider first the command eval. So, we'll see the help text. If I run this, and it will be in the MATLAB window. Here it is. So eval executes a string with a MATLAB expression. And eval expression evaluates the MATLAB code in the string expression. Let's go back to the editor window. And I'll quote again, eval on an expression evaluates the MATLAB code in the string expression. Why would we want to do this? Well, the answer has to do with the order in which MATLAB evaluates the objects it encounters. And this is perhaps best explained in the context of defining and using anonymous functions. For example, you know that you can define a quadratic function, consider t squared minus t plus 1, in MATLAB via the @ syntax. So this is how you define the anonymous function t squared minus t plus 1. And that's why, incidentally, in the MATLAB window, you saw at the bottom there, f. Okay, let's go back. Now, what can you do when you do that? You can evaluate the function. So we can evaluate f at 1.5. And if I do that, the answer is 1 3/4. That's what happens when you evaluate the polynomial at 1.5. You can plot it with EasyPlot. We run that. There's the plot of the quadratic function. Looking at the MATLAB window, let me go back to the MATLAB window. MATLAB would have preferred to run EasyPlot on a vectorized function, so we can also vectorize the function, and I've done that here. So it's the same function, but vectorized, and I EasyPlotted it this time on -5, 5. So there's again. Okay. Now, here's the point. Sometimes the function you want to evaluate or to plot arises from a preliminary computation. For example, as the derivative of another function. So here's a situation where you've got g as a cubic function, and f is its derivative. Here I called it f2. Since we're using symbolic differentiation, I first define t as a symbolic variable. So let's run this. And as usual, look in the MATLAB window. And there's our differentiated function. f2 is the derivative of g. Okay, but now let's evaluate that function at 1. If we go back, let's predict what it ought to come out. It's this quadratic. At 1, we should get 3 minus 2 plus 1, so we ought to get 2. Let's see what happens when we evaluate. Run the section, look at the MATLAB window, and what happened? We didn't get the right answer. So why didn't we get the right answer? The reason is because f2 is not the function 3t squared minus 2t plus 1, but rather the expression 3t squared minus 2t plus 1. And you can check that that's the case by using subs, which substitutes a value for a variable in an expression. And if we do that, you'll see that we then get the value 2. Nevertheless, we may want to use f2 as a function, and that's where eval comes in. If you want to treat f2 as a function, you can accomplish that by using eval. So here's f3 defined to be the same as f2 but evaluated, and then you'll see what happens when we evaluate that function at 1. Looking in the MATLAB window, there it is. We get the right answer. So that's the way eval is typically used. It's often used in little programs, but let's give it an application. So I'm going to use it to consider a streamlined version of problem 7 in problem set B from Doom. That problem asks the reader, the student, to solve this first order equation. Okay, I'm going to do it with dsolve in a minute, and dsolve actually gives the solution in implicit form. And then you're asked to plot the solution that satisfies y of 2 equal 1.5. And for that solution, find y at 1. So here's the solution. Clear everything. Define t and y to be symmetric. Here's my equation. E to the y plus t to the y minus sine y, y prime is 0. And then I dsolve it. Let's see what happens. So the answer is an implicit function. Cosine y plus t e to the y equals constant. It can't solve that explicitly for y as a function of t. So I then define f to be that function of two variables, the implicit solution. Let's go back to the editor. MATLAB can't find an explicit solution. It does find an implicit solution, and so the solutions of the differential equation are f equals c, where f is this function here, cosine y plus t e to the y. Now, I want to find, so going back to the statement of the problem, plot the solution that satisfies y of 2 equal 1.5. So the solution that goes through the point 2, 1.5. So we need to do that. I need to find the value of c that f equals when t is 2 and y is 1.5 in order to get the contour that goes through that point. So that's what this is. These commands are structured to do. I compute c, draw the figure, and let's do that. So there's the curve. Notice when t equals 2, y equals 1.5. Blow that up a little bit. Right? When t equals 2, y equals 1.5. So there's the solution curve to the differential equation, which goes through the point 2, 1.5. And we're asked to find the value of the function when t is equal to, I believe it was 1. Okay, so this value up here looks like something between 2 and 2.5. Okay, so for t equal 1, we want to find the solution of fty equals c, with c is above. And so I'm going to use f0 for that, and I'm going to get into trouble with f1 defined here unless I use eval. So that's the reason for these two commands. F1 gives me my functional value, and y1 is the value of that function at t equal 1. Let's see what comes out. .2698. Let's look at the graph again. I actually marked them. So there's the initial data, and here's the value of the solution function when t equals 1. Okay. That's what these last two commands here. Plotted those 2 points on the curve. So my last point here is I suggest you try the command above without using eval and see what happens. Okay, now let's pass on to our second command, deval, right here, and see what we can learn about that. Again, let's look at the help text. So help deval comes up in the MATLAB window. Here it is. It's a bit long. But basically, it evaluates the solution of a differential equation problem at the entries of the vector x in it. So you can basically instruct MATLAB to look at a problem where it's already applied a differential equation solver, like ODE 45, and tell it to evaluate the solution at a certain specific set of points. Okay. So let's illustrate this. I'm going to look at the differential equation yy prime plus y plus 1 squared equal t with the initial data y of 1 equal 1. Let's first of all see whether we can solve this symbolically. So let's put dsolve on it and see what happens. It's grinding a bit. Okay, let's see. Sorry, no cigar. Empty sum. MATLAB cannot solve it symbolically. So we have to work numerically via ODE 45. We can easily plot the solution as well as evaluate it at certain values, but in the latter case, MATLAB picks the values. We can use deval to override those choices and evaluate the solution at the points we prefer. So let's see how that goes. First, let's do a graph. So I first defined f to be the right-hand side of the differential equation. There it is, when I solve for y prime, of course. And then I did ODE 45 on it. I graphed it on the interval 1 to 5, and the initial data, remember, was y of 1 equal 1. Right, that's here. So that's the reason for this. Let's evaluate that. There's the graph. Right, starts out over here at 1, 1, decreases, turns around and starts to increase, and looks like there's some sort of minimum at roughly t equal 1.5, and the minimum value is roughly 0.2. Okay. So again, it says the solution decreases from its initial value 1, 1, bottoms out at approximately t equal 1.5, with y approximately 0.2, and then it increases. We could get more information about the behavior as t increases by increasing the length of the solution interval. I only went out to t equal 5 here. But I'm not so interested in that. I'm much more interested in the behavior of the solution near what appears to be a local minimum. So let's hone in on that point and see what values MATLAB supplies. So I changed the default digits to 16, and this time I'm only going out to 2. And I'm not going to plot it this time. I set the values of ODE 45 into a vector, and we're going to see what numbers come out. So we'll see which values of t MATLAB picks and what the corresponding values of the function are. So if I run that and look in the MATLAB window, there we are. There's all the approximate values that MATLAB computes. Started out at 1, 1, and as t increases, y is decreasing, keeps decreasing until about here, right? Is 0.217, 0.211, no, it's still decreasing, 0.210, and then it going back up. So it's somewhere around 1.466. And the other thing to observe is that these guys are incremented in their step sizes of about 0.02. Right? There's about a 0.02 difference between the t values. So I have an approximation, but I think I can do better by choosing the values at which the intermediate values at which the solution is computed. Okay. So again, the smallest value that MATLAB supplies is at this number, 1.466, etc. And as I observed, the separation in t values is about 0.02. So I'm going to use deval to, deval to refine the data. Okay, so first we must assign the output of ODE 45 to a structure. So that's what I've done here. And then I tell MATLAB to access that structure and look at all the values of t between 1.465 and 1.467 with step size 0.01. Let's do that. And now what have we got? So there's 21 values there. And if you stare at them long enough, you see where the values turn. Let's see, 210, 4466, 4466, 47. So it's between this third one and fourth one where it turns from going down to going back up. And so, as we say here, remember here was the values, so it's between the third and fourth. So 1.4653 is a better approximation to the local min than the original result that was supplied by ODE 45, in which MATLAB selected the intermediate values. You can get more digits of accuracy by refining the choice further in the values you select for a dval. Okay, we will apply dval in the solution of problem 10 in problem set D, but in fact that's a boundary value problem rather than an initial value problem, and so I'm going to first look at BVP for C before I actually supply that example. So continuing, we're now going to look at BVP for C. I'll let you look at the help text by, of course, typing help BVP for C. It's a little long. So instead I'll give a quick explanation and refer you to the material on page 154 in Doom. So let's consider a boundary value problem. So here's our differential equation. It's a second order linear non-constant coefficient equation, y double prime plus t squared y prime plus y is 0. But instead of being given the value of y and its derivative at a point, say 0, we're given the value of y at two distinct points, 0 and 1. What we've usually called a boundary value problem. And MATLAB has a boundary value problem solver, BVP4C, and it's a little complicated, but it requires two auxiliary objects, a so-called preprocessor, which is called BVP init. It basically sets an initial guess for the solution, which in this case we're just going to take to be the constant vector 1, 0, and then a function called bcond, or bcondition, boundary condition, of YA and YB, which when set to 0 specifies the boundary conditions. Okay, here's the code. As usual, I clear things. The right-hand side is the differential equation reformulated in the form of a system, usual way, right? Y1 prime is y2, and y2 prime is the right-hand side of the differential equation. This is what y double prime equals. We apply the preprocessor, and this is our initial guess for the solution, and there's the boundary condition. YA1 minus 1, so this is 0 at 0 and 0 at 1. And then we set BVP4C on it with these two preconditions. We set up a vector between 0 and 1 with step size 0.025, and we tell via dval that that's where we want to evaluate the solution, the boundary value solution, and then we will plot it. I'll evaluate this in a second, but as above, with sol, BVSol is a structure, and dval tells it to evaluate the solution at a regular set of points. If we do this, there's the curve. Right? 0 at 0, 1 at 1. As was specified in the boundary value problem itself. Right? Look back. There it is. Y of 0 is 0. Y of 1 is 1. Okay. All right. Now let's use these two, BVP4C and dval, to solve part B of problem 10 in problem set D. Here's the problem. The longitudinal displacement in an elastic bar of length 1 is given by the following boundary value problem. AX u double prime plus A prime u prime equals f of x, u of 0 equal u of 1 equals 1, and A and F specify the physical properties of the bar. So in this problem, you're asked to take A equal 1 plus x of x, and f of x is 5 sine squared of 2x. So this is like a rod, which is growing more dense to the right, and then you've got this kind of sinusoidal force, which, if you think about it, sort of mimics what you'd have if you had a gymnast holding onto the bar in two different places. So there's my differential equation written as a system. Same commands as specified above. I solve between 0 and 1 in step sizes of 0.005, and let's see what the bar looks like. Right? It's denser as you go to the right, so it's not as elastic, and so there's one hand and there's the other hand, but because of the inelastic properties of the bar stretches more on the left-hand side than the right-hand side. So I've now illustrated the boundary value solver, BVP for C, and another use of dval. Okay, let's turn now to our fourth and last command, deal. We'll begin by looking at the help text, which tells us that deal's inputs to output simply matches up the input and output lists. It turns out this is most useful when the number of outputs differs from the number of inputs. And we'll see exactly how to make use of that in a moment, particularly to replace a function M file by a single line in an event detection problem. So as I say here, it may not be immediately evident how to put this command to good use, but here's one example that illustrates, motivates the use in one of the problems from problem set F. So we use the command to create a one-line function that converts a pair of polar coordinates to this corresponding pair of rectangular coordinates. So rectangular is the function of two variables, r and theta, which deals these two. So it automatically sets up a vector with two components, and the first component is here, which of course is just the x component of the polar coordinates, and the second one is the y components of the polar coordinates. So just to illustrate, so here I'm going to compute the rectangular coordinates of 1 and pi over 4. That's on the circle of radius 1 at an angle 90 degrees. Should be 0, 1. Let's see. Run the section and look in the MATLAB window. Pi over 4, 45 degrees, right? So there's my function, find via deal, and here's the conversion of 1 pi over 4 and polar coordinates to rectangular coordinates. It's basically the point square root of 2 over 2 in both in x and y coordinates. Okay, so I say here, you can compare this with the example on page 119 of Doom, where it required a function M file to essentially do a similar chore. So I urge you to take a look at page 119, and you can see how we've avoided the use of a function M file by using deal. As it says here, the video is somewhat long, so I'm going to conclude by referring you to the solution to problem 6 from problem set F that actually appears in the Doom book. It's on pages 269 to 276. But especially the material on page 276 for a utilitarian use of deal. It's used to define a one-line events detection function, and it thereby avoids the extra event detection file that is normally required for the options/ODE set aspect of the event detection procedure. Finally, I note that there are many other MATLAB commands that you might find useful in solving the problems in Doom. Most, but not all, are discussed in the book itself, but you may also consult an online glossary which can be found at this URL. And I find lots and lots of MATLAB commands. And if you explore them, you might find others that you might make use of in your solution to some of the problems from Doom. So I copped out a little bit here. I didn't actually give you another. I didn't give you another solution of problem set 6 from problem set F. But I urge you to take a look at page 276. Thanks.